Thanks, Jason, for the flattering introduction. So a little bit more detail of who I am. I'm basically a core committer on Apache Spark. For those who do not know what Apache Spark is, don't worry, I'm going to explain all of that. And also the lead developer of Spark Streaming. I was in a PhD program in Berkeley last semester, but I'm on leave right now. And I'm here right now to talk about Spark Streaming. Now, even before Spark Streaming, let's just start from the basics that big data. I'm sure all of you have heard this buzzword. It's being thrown around all the time. Specific in big data, today I'm going to talk about big streaming data. And basically, you know that there are lots of high volumes of data streams that are floating around right now. There's Twitter stream, there's streaming data from sensors, there's streaming data from distribution networks. There's lots of streaming, high volume streaming data that needs to be processed in real time. For example, you may want to do fraud detection on continuous bank transaction and find out fraudulent transactions as soon as they happen. And you really need to find those as fast as they happen, otherwise the harm is already done. Similarly, there may be anomalies in the sensor data that you might want to find again fast so that you can react to it and fix the sensors or whatever. Or you might do something much more trivial and find cat videos on tweets. That also works. But that's also big data. So how to process these large volumes of streaming data? And what we essentially need is a distributed processing system, which is basically a cluster, a framework that is running on a cluster, which takes this large volume of tweets or any data stream that you like, and it gives out the processed results. Now, what are the characteristics that we need from this distributed processing system? It needs to obviously be scalable, scales to hundreds of nodes, achieve low end-to-end latency so that you get results fast. You also need things like efficiently recovering from failures, as well as something we valued a lot from our geek experience in production environments is something that integrates well with batch and interactive processing systems. Now let me elaborate on that. Why? So what have people been doing till now in building these kind of systems? And what people have mostly done is they build these sort of two independent parallel big data stacks. One for batch processing, like using Hadoop MapReduce, etc. Another, they build their streaming stack either using their own custom home-based streaming system or things like Storm, etc. that has been gaining popularity lately. Systems like this, they build two different parallel stacks, which often process exactly the same data. One processes in real-time fashion, the other processes larger volumes in more batch-like fashion, let's say, to generate weekly reports and stuff. Now, why two different stacks? Because none of the existing frameworks, well, until now, with Spark Streaming, none of the existing frameworks till maybe last year could handle both kind of processing requirements. So some frameworks like Storm could either do stream processing with hundreds of MB per second throughput with low latency and stuff, or frameworks could do high volume batch processing on terabytes, petabytes of data like Hadoop MapReduce. But not a single system that can be tuned to do both. And what is the side effect of having these two dual stack system? Each of these different frameworks have different processing models. They have that you need to learn, you need to understand, you need to express your business logic in different processing models. That doubles the effort of implementing, doubles the effort of solving bugs, doubles the effort of maintaining consistency across these different models if you're doing the same computation on both these stacks. And obviously, from operational point of view, you have to deal with the managing two different frameworks, each of which usually has its own different idiosyncrasies and stuff. So in short, it's not exactly a simple thing to do. Enter Spark Streaming. And what essentially it is what it does is this is a system that receives data stream from many different standard input sources like Kafka, Flume. We recently added Amazon Kinesis support, Twitter, of course, and plain old HDFS or HDFS compatible systems like S3. Takes data from them, processes them, munges all the data that you want, and pushes the data out to storage systems, HDFS, database, NoSQL systems like Cassandra, HBase, and maybe update dashboards directly and things like that. And this whole system is scalable, fault-tolerant, and achieves end-to-end latencies of the order of seconds. Let's dig deeper. How does it work? So essentially, if you open up Spark Streaming, inside you will find that there are essentially two things. One is a set of receivers that receive the data. As they're receiving streams of data from outside, it chops it up into small batches of data and hands it off to the second component, which is essentially the Spark processing engine. Actually, let's have a show of hands. How many of you are not familiar with Apache Spark? Well, actually, quite a few. Okay, that's good. Then this is probably the appropriate time to do a little bit of introduction on Spark. So what is essentially Spark? As you can see, I guessed that there might be people. I have the next slide ready. So Spark is essentially a very fast, general-purpose cluster computing framework that is interoperable with Apache Hadoop, MapReduce and stuff. And it's a very general purpose, allowing all different kinds of computations, and it improves the efficiency of the computation over Hadoop MapReduce-like systems using two features. One is in-memory computing primitives. It allows you to keep the data around, keep large volumes of data around in memory that can be processed over and over again. And it exposes a very general computing engine, not just MapReduce. By the way, how many of you are not familiar with MapReduce? Okay, that's good. Okay. I didn't have any slides on MapReduce. I would have been in trouble if anybody said, okay, no MapReduce. Okay, good. Beyond the MapReduce, very restrictive model of MapReduce, Spark allows general computation graphs. And in terms of usability, it improves the usability of MapReduce simply because you can write programs in Spark in Scala. That itself is a big deal, which I don't need to convince you guys. And what it also provides is it extends we provide something called a Spark shell, which extends the Scala shell and allows you to interactively query big data over a cluster in the background, interactively at the scale of seconds, just like you use a Scala shell. Now, I will not demonstrate this fact Spark yet because in the interest of time, I want to focus on Spark Streaming. But let's see what are the benefits of this. So, for example, this in-memory computing and this general computation that improves performance in terms of your job processing times up to 100x compared to MapReduce if your data is in memory, or 2 to 10x compared to MapReduce even if your data is not in memory but on disk. And in terms of usability, of course, it allows you to do really fast, interactive, big data processing on the fly using your familiar Scala shell environment. Now, what is the programming model behind Spark? It is this thing called Resilient Distributed Datasets, or RDD. And RDD is nothing but a distributed collection of objects. Now, essentially imagine it's as a huge array which is partitioned across multiple worker nodes in a cluster. And now you can, these are essentially like sequences in a very, if you compare it with Scala, these are essentially like sequences, but and you can essentially do these sort of flat map kind of parallel manipulations, except once you apply these sort of functional operations, that gets executed on a cluster. So that is the big difference. And these data sets can be cached in memory on the worker nodes. I'll walk through an example to better explain it. And another fancy thing about these RDDs is that you're keeping the data in memory. In a cluster environment, your machines can die, or in a cloud environment, that is often the case. The RDDs have enough information that it can recreate itself and restore itself in memory if any part of the RDD is lost because of machine failures. So these are the very important characteristics that allows RDD as a very strong programming abstraction for processing big data. Let's walk through a very example of, let's say you want to have a large log file and you want to process that log file interactively to find out error messages in the log file and find out patterns and stuff. So what you will do is you can do it either in a standalone program or in the Spark shell. Here is let's say this is the cluster environment that you have, 1 driver, 3 workers. On the driver node, you'll basically be running the Spark shell. and you'll do something like this. Say Spark text file. You open up a text file which is sitting in HDFS, and what this line does is essentially creates this base RDD called lines. And these lines represent the data that is sitting in the HDFS file. Next step, we apply this, let's say, filter operation, and we want to find only those lines which start with error, and which creates another transformed RDD, errors, which essentially contains only the lines that start with error. And next, maybe we want to do further stuff like split each of the lines by tab and things like that, and extract out the second columns, etc., etc. And then we also, let's say, we want to process this set of this final RDD messages over and over again, as in run many queries on top of it. So why read it from the data over and over again? We'll just basically ask the system to cache it in memory, so that further queries on that is going to be much faster. Now, while the system is actually executing these lines, on the cluster, nothing is happening. It's essentially all lazy. So the drivers and the worker are just sitting idle as of now. Only when we actually ask for some result back, let's say filter these lines and give me the count of how many lines are there that matches this in the file. We want a result back, and count is essentially what we call an RDD action. Once we ask the result back, does the driver actually go ahead and do something? It actually figures out where in the HDFS, where the data is present, in which workers it is present. It sends out tasks to the workers, similar to the MapReduce fashion, but in a more efficient way. All the workers read the blocks of data, execute the tasks, and finally give back the results, which in this case is count. And the driver gives back the result finally into your program. Now, also what is happening in parallel is that since we have asked the messages RDD to be cached in memory, the system actually caches the materialized messages, partitions of the message RDD in the memory. So that when we execute another line, let's say on the same RDD, it doesn't need to read the data from the blocks again. It can just read it from the in-memory cache and give back the results much faster. And using this, we can, once cache in memory, the performance difference compared to Hadoop MapReduce can be of the order of 100x. And you can process, we have done things like processing, querying 1 terabyte of data on 100 machines within a matter of 5 seconds or 7 seconds. So we have done pretty good benchmarks on this. And because Spark is such a generalized computing platform, it is essentially the computing engine behind a whole slew of other components being built on top of Spark. Spark streaming being just one of them. There's Spark SQL, which is essentially SQL processing, SQL querying on big data. There is machine learning libraries, MLlib. There's graph processing algorithms, GraphX, all being built on top of Spark. Anyways, going back to Spark streaming, there's this essentially Spark streaming essentially has this Spark sitting inside it. Streaming hands out all these the data stream in batches to Spark. Spark does all its usual processing that it does, and then finally gives out the results in batches. And for Spark streaming, there is a higher level programming model called D-streams, which essentially represents a stream of data. And underneath, in the system, it is essentially implemented as a sequence of these RDDs, as a continuous sequence of RDDs. I'll explain the example in the next slide. And the nice part is that the dstream API is very similar to the RDD API. It's the same functional MapReduce kind of API. And you can create input dstreams from different sources and then apply these MapReduced parallel transformations to create more dstreams for transforming the data. Let's walk through a very simple example. Let's say we want to get all the live hashtags from Twitter right now. And what we will do is essentially first start something called a streaming context, which is essentially the starting point of all the streaming functionality. And using the streaming context, first we'll create something called input dstream tweets using these Twitter utils functionality. This is all inside the Spark streaming programming model. You can just go to the website, no need to learn all this code on the fly. So it's all there. So input this stream. What essentially the system underneath will do is that it will go to the Twitter streaming API, get the stream of tweets from Twitter, and chop it up and divide the data into batches and store it in the memory as RDDs. Then, plus it will also replicate the data in memory for fault tolerance and stuff. I will not go into those details here. Let me focus on the high-level basics. Next, when we apply these sort of functional transformations like flat map and stuff, it creates new D streams, and the system underneath, what it does is that corresponding to every RDD in the parent tweets D stream, it applies the same functional transformations on each of those RDDs. It creates a new sequence of RDDs. The new sequence of RDDs essentially becomes a new D stream. And then again, you can keep doing these transformations. And finally, let's say you want to do something with the data. You want to push the data out to, let's say, some file system and some into a text file or something. So there you can do these sort of output operations like save as text file, where each batch of data will be saved as a text file onto any HDFS compatible file system. And the system underneath will take every RDD and save it. Not just saving to file, you can do arbitrary stuff with the data. And there's this simple primitive for each RDD that gives you direct access to the RDD environment. And once you have this RDD, you can write arbitrary Spark code, raw Spark code to do whatever data you want to do with the data. You can directly push the data out to Cassandra, let's say. You can push it out to HBase. You can directly update streaming a dashboard UI in real time. Whatever you want to do with the data, you can do with it. Also, besides the basic map, reduce, etc., there's some additional functionality that comes with DStream, and some of these are called window-based transformations. What it essentially is that you have a stream of data. What this allows is essentially a sliding window operation on the data. And in this case, in this example, basically what you want to do is that count all the values in the last 1 minute of data every 5 seconds. And so as you can see, there are like essentially two parameters. What is the length of the window, how much data to aggregate together, and how fast should the window move every 5 seconds in this case. And so there's like variations of this window operation where it's window-based aggregations like reduce by window and count by window and things like that. Also, there's you can do arbitrary stateful computations. Let's say, for example, you want to monitor the whole Twitter stream, and let's say for every user, you essentially want to maintain what mood the user is in. Essentially, you're trying to maintain state for every user. Well, it actually sounds creepy, but let's go with the example. So let's say you want to maintain this state on a per user or a per key basis. What you can do is essentially give this simple function that given the previous state of the user, previous mood of the user, the new tweets that he has made, what is the new mood of the user. You give this function to the system and apply it on using this transformation called update state by key, and the system will keep updating the state for all the users as data keeps coming in. And it's very functional, obviously, and the system just takes care of it by itself, of applying it on large volumes of data streams. So this allows you to do very arbitrary stateful computations out of it without requiring any external system for fault tolerance and stuff. And even more stronger thing is that, and which shows what is the advantage of having this very streaming API, which is very similar to a batch API of Spark, is that you can very easily intermix all these RDD and DStream operations. Like for example, let's say you have a file which has all the data, let's say information about spam tweets, and you want to take the Twitter stream, the full high volume Twitter stream, and you want to join it with with this spam file to filter out the spam tweets out of it. Basically, you're trying to take a stream and use a file to filter it out. That is not something that is very trivial to do in any other processing systems like streaming systems like Storm or even home-baked solutions. It's not very trivial to do this in a fault-tolerant way. But here you can do it very easily using this transform operation, which gives you the RDD. Here is the RDD. Do whatever you want with that RDD, like join it with another file and things like that, and it will keep doing it on the fly. So this gives you a lot of power. For example, what you can do is essentially in the same system, Spark plus Spark Streaming, in the same platform, you can take, let's say, compute statistics on historical data over last 1 month or 1 year of data, and take that statistics and apply it on the live data stream. Build models on historical data and apply it on live data streams. You can combine streaming with other components of the Spark stack, like machine learning algorithms and graph algorithms, and do things like offline learning, online prediction, then online learning and prediction as well, simultaneously learning the data that is coming in and predicting using the models learned continuously. And you can also do things like combine interactive querying with data stream, like for example, interactively query the streaming data using SQL. And in fact, let me actually show a very quick demo. I think time permits me. So a very quick demo of how this sort of actually looks like. And to show the demo, let me actually segue into something that my company, as in not my company, the company I work for, Databricks we are building is this, let's actually start from the scratch, is this cloud platform that we're building, which basically takes the open source Spark platform. So by the Spark, all of it is open source. If I forget to mention, just be clear that all of Spark and Spark Stream and everything is open source. But what we built on top of Spark is this integrated development environment, which is a managed hosted Spark environment that allows you to create Spark clusters on the fly and then do interactive data visualizations using that. And for example, here in this, this is essentially the Databricks Cloud Platform. Here we can build workspaces, like for example, I'm going to do, let's say, this is essentially the Spark shell running in fancier UI. And you can do simple Scala stuff as well, of course. There is, sorry. Oh, crap. That's, yeah. I think that is better. Is that better? Okay. Yeah, better than what was earlier, of course. So, for example, I have a cluster running, which is a kind of a small cluster with 16 GB memory just for the demo, but I can very easily create clusters. I can say my new cluster, add it, let's say 8 GB or 10 GB memory, and create a cluster like this, etc. And it'll automatically create the cluster for you and prepare it that you can directly start running Spark. You don't need to do all the management of actually creating clusters and stuff. Anyways, my focus is on Spark Streaming in this talk, and so what I'm going to do using this is that I already have a cluster setup, as I showed, and what I'm going to do is actually run a Spark Streaming program inside it to show that how it actually look and feels in that. So let's say first I'm going to actually import a few functionality. Import. Let's see. Okay. So what I can do is using this is I can actually upload libraries. So for example, if you have written your custom library code, I can use that. I can actually upload that as a jar and use that in my program. So that's what I essentially do. I have some basic functionality out here, like getting Twitter authentication and stuff that I have written in a jar. I'm going to use that. Okay, this is going to be slow. This I did not expect. Okay. Okay, let's actually try something else on the fly. Well, I cannot run the program for obvious reasons, but what I was going to do is essentially create the Twitter stream, and here for each of the batch of data that is generated by the Twitter stream, it actually I can take the RDT and register it as a table, and Spark directly supports that using this Spark SQL platform as a table, and then I can apply SQL queries on top of it. Let's head back to the slides in the interest of time. So what I was going to demo was essentially on the sample Twitter data, which is a very small amount of data, but instead, but you can actually, we have actually tested Spark streaming on very large volumes of data. We have processed like 16 million records per second, which is like 6 GB per second at scaled out to 100 nodes, all with a sub-second end-to-end latency. So it is really scalable, fault-tolerant and stuff. And also another advantage of a unified stack using Spark and Spark streaming is that you can very easily transition between different modes. Like for example, let's say you have to actually figure out, analyze the data and figure out in patterns like this. So you can use a Spark shell to take small amount of data and figure out some pattern, then take apply that the algorithm that you have figured out to figure out the pattern on much larger volumes of data, either by writing a standalone Spark job and running it on 1,000 machines. And then, and once you have written that Spark program, you can take essentially the very similar Spark program and convert it to a Spark streaming program and run it on live data stream as well. It's very easy to transition between different modes. Anyways, to conclude, so Spark streaming comes packaged with Spark, so just go to the Spark website and search Apache Spark and you can get the website. It takes really 2 minutes to download and try it out locally, and you can very easily create an EC2 cluster out of it, and so you can actually test it out on an EC2 cluster. We have a very active Spark mailing list where people are very active about answering questions and helping each other out. And look at the programming guide for more information. Thank you.